Okay, so I welcome you all again in this radiation lecture series. So we were studying that how to find the net radiation heat exchange between any two surfaces in a discrete enclosure or at any part in a continuous enclosure, right? And I told you that there are mainly two methods by which we can do that. The first method is by solving simultaneous equations, and we have already seen that how can we do that for both an enclosure, I mean for both a continuous enclosure and a discrete enclosure. And by this time you already know that what do I mean by a continuous enclosure and a discrete enclosure, right? And you also know that why do we call this as the method of simultaneous equations. So we get from these equations, so this is for the enclosure having all black surfaces, this equation. So if we have n number of black surfaces, then for all i's, I can be 1, 2, 3 dot 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 up to n. So for I surfaces, so sorry, for n surfaces we will have n equations, n linear equations. So we have to solve those equations. Okay, and we also told that we will be asked mainly to find either the heat flux or the temperature. So heat flux is here and temperatures are here. EB are sigma T to the power 4. EBI is equal to sigma Ti to the power 4. So that is nothing but the temperature. So now this video will be very short. I will be just showing you the method of electrical analogy. Okay. So I should give this a heading. Okay. Electric circuit analogy of radiation heat transfer. Heat transfer. Okay. In or okay, among not every surface, gray, diffuse, okay, or black, okay, or I should say okay, or black surfaces. Okay, so this is the heading of today's lecture. So I know many of you already know this one, okay, because for gate people use only this one because this is more convenient, and this is a, I should also say, this is a time saving approach. Okay, so let us see. So if we directly see two surfaces, okay, so here we will take the opposite approach. First we will go for two black surfaces, okay, two black surfaces, okay, and here I will consider plane surfaces also, okay, two black plus plane, okay. So if I say it is a plane surface, then it directly indicates that my Fii is equal to 0. Clear? So if my Fii is equal to 0, so now let us see. First let us consider two surfaces. Okay, so this is my surface 1. Okay, it is having temperature 1, sorry, temperature T1, and this is my surface 2. This is having temperature T2. Clear? and both these surfaces are black surfaces. Okay, both both of these guys are black. Okay, so now I will ask you that I have given you the temperatures T1 and T2. I need to find Q1 and Q2. Okay, now in steady state we can directly say that Q1 is equal to minus Q2. Okay, otherwise there will be some, if 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 this is not the case, this one, the temperature will increase. Okay, so here another assumption is, that is HOI. Okay, HOI is equal to 0. That is, there is no external heat or external radiation energy that is incoming from outside. Okay, no, there is no external thing. Anything, if there is any heat, if there is any heat interaction, that is by radiation heat interaction between these two surfaces. So we already know that Q1 is equal to J1 minus H1. So let us assume that heat is going from this to this. Okay, so this is Q1 and this is Q2. Okay, so Q2 is equal to minus Q1. So that means I am assuming that my T1 is greater than T2, or my T2 is less than T1. Okay, so if that is so, now let us see, Q1 is equal to J1 minus H1, right? So now what is my J1? J1 is epsilon into epsilon 1 into EB1 plus my reflectivity rho into H1, right, minus H1. Okay, so now for black surface, epsilon 1 is equal to epsilon 2 equal to 1. So that means this will be EB1 plus rho means what? 1 minus alpha. Rho is reflectivity, this is 1 minus alpha. So EB1 plus H1 minus H1 alpha minus H1, that means it is EB1 minus alpha H1, right? Now if I consider that if it is a diffuse gray surface, then my alpha is equal to epsilon. So these are very subtle points, that are, this alpha is equal to epsilon. This is only valid for diffuse and gray surface. Okay, otherwise not, right? So that means I can write this as EB1 minus epsilon H1. However, okay, however I know that okay, now this is fine, right? So this is my, okay, now epsilon is equal to 1, so that means it is EB1 minus H1. I should write this as alpha 1 and this is my epsilon 1. Okay, okay, that is fine. So you see that here I have got my J1 minus H1 is equal to epsilon 1 minus H1, right? That means I can directly say that my J1 is equal to EB1. Okay, and this I already know, right? This I already know, that is my J1 is equal to EB1 for a black body, because for a black body, my what? A black body absorbs all the thing. So for my black body, alpha is 1. I mean, even if I don't use this assumption, my alpha is directly 1 for a black body. Okay, so my J1 is equal to EB1, and if my H1 is equal to 0, if H1 is equal to 0, so I can directly write, so the conclusion is, for a black surface. Okay, Q1 is equal to EB1 minus H1. Okay, and also I can write my J1 is equal to EB1. Okay, now it is fine. Now what is my H1? So I have already told you that I can write actually my H1 is equal to HO1 plus, okay, so here there are only two surfaces, so I can write J2 F21, okay, only this one because it is per unit area. Okay, now you can again I can see that my J2 is equal to EB2 because my surface 2 is also a black surface. Clear? And if I say my HO1 is equal to 0, then it is EB2 F21. If my HO1 equal to 0, HO1 means what? External radiation, or directly I should write external irradiation on surface 1. Clear? So my H1 is equal to this. Now let me write Q1 is equal to EB1 minus EB2 into F21. Okay, so this is my direct equation. Now I can write my EB1 equal to EB1 into F21 plus F22, right? So this will be EB2 F21. Clear? So that means I have already told you that because these are plane surfaces, my F22 is equal to 0. So this becomes EB1 minus EB2 into F21, or I can also write EB1 minus EB2 into F12 into A1 by A2, right? Okay, so I can see that my Q1 is equal to, okay, or if I directly write, okay, so here it will be good if I multiply a A2 here. Okay, that doesn't matter. Now this is my Q1, okay, and this is equal to minus Q2, right? So Q2 is equal to EB2 minus EB1, okay, into F21. So that means my capital Q2 is equal to A2 into EB2 minus EB1 into F21, right? So this is equal to EB2 minus EB1 by 1 by A2 F21, and this is also equal to EB2 minus EB1 by 1 by A1 F12. Clear? So that means, and this is actually equal to minus Q1. Clear? So if I have two black surfaces, then this is like the Ohm's law. Okay, so my voltage difference, now I can write my voltage difference EB2 minus EB1, I can give a mod here, okay, this is equal to, okay, mod of Q1, okay, into mod of Q1 into what, into 1 by A1 F12 and you can also write mod of q2 into 1 by a2 f21, and I mean you can always play with these things. Okay, now if a1 and a2 are equal, then these will not matter, but if a1 and a2 are not equal, then these will matter. Okay, I mean you are putting which thing where. So how can you memorize this thing if you are appearing for gate? You see, my net heat exchange q is equal to, okay, eb1 minus eb2 by 1 by, so if you are considering a particular surface, okay, so here we are considering that my heat is transferred from surface 1 to 2. So this is my net heat exchange from surface 1. If this is 1, I will write here a1, area 1, f12. Okay, so I can draw like this. So this is a point, here I have a resistance, it's another point. So here the voltage is EV1 and EV2 here, and in between I have the resistance this, and that is equal to this A2 F21. Clear? So this is the radiation network analogous to the electrical network for a black body. Okay. Now if you have so many surfaces, then the I mean radiation network will be changed. For example, if you have, let us say, 3 surfaces. Okay, so if you have 3 surfaces, so each at temperature T1, T2, T3, no two of them are equal. Okay, so here how can you draw it? Very simple. That is, for surface 1 you have to draw a node, right? For surface 2 you have to draw a node, for surface 3 you have to draw a node, and every surface is exchanging radiation energy, right? So this EV1, EV2, EV3, clear? And in between that you will have R13, R12, R23, where I can write Rij is equal to 1 by Ai Fij is equal to 1 by Aj Fji, right? Okay. Now this resistance has a name. Okay, this is called the space resistance as far as I can remember. Okay, I apologize to you that I don't remember the actual name. So we called RSP. This is, I think, the space resistance. Okay, so this is the space resistance. So now let us directly go to the second thing, that is the for a non-black surface. Okay, so for a non-black surface, and also gray diffuse surface, okay, for a non-black gray diffuse surface, so see, what you have to build is the net heat exchange between any two surface. If you can build the expression for any two surface, or if you can build the radiation network between two surface, you can build between any number of surfaces, because if you have an enclosure like this having n surfaces, then you can easily make it, because I mean obviously the network will be a bit complex, but see, you can have, so let us say that we have 5 surfaces, so 1 2 3 4, okay, and 5, okay, so for this surface it will have a connection with this surface, with this surface, with this and with this, and if it is a convex surface, the I mean convex or sorry, if it is a concave surface like this, it will also have a network with itself. Okay, but here we are considering only the planar surfaces. Clear? You can always consider a non-planar surface also. For that we have a general correlation. So so I should give you a word of caution that this radiation network analogy is mostly suitable for the plane surfaces. Okay, and if you have non-planar surfaces like a cylinder inside another cylinder, a sphere inside a cylinder, a sphere inside a box, a cylinder inside a box, a sphere inside a sphere, then go for this equation, I mean this simultaneous equation thing. Okay, because you see I have done all these things considering Fii is equal to 0. Okay, so strictly this radiation network analogy is for the non-concave surfaces. It has to be either a planar surface or a convex surface. For that only Fii is equal to 0. Fii is also called self-view factor. Okay. Now for non-black gray diffuse surfaces, let us see how can we do that. So this is having a temperature T1 again, and this is T2 and this is less than T1. Now for a non-black gray diffuse surface, let us see that we already have shown that for a black surface, for a black surface, my J is equal to EB is equal to sigma T to the power 4. But for a non-black surface, right, what I will have? I will have my Q. Okay, so leave Q aside. Let us focus on J first. So J is equal to epsilon into EB, okay, plus what, rho into H. Now epsilon into EB plus 1 minus alpha into H. Now if I further consider what? Further consider gray and diffuse surface, then this will boil down to what? J is equal to epsilon into EB plus 1 minus epsilon into H. Clear? Okay. So that means this is epsilon, okay, it is fine. But I can see that here J is at least not equal to EB. There is J is at least not equal to EB, right? So, okay, so now let us see another analysis. So see, Q is equal to J minus H. We have this equation. Again, we can have one more equation. I have done this analysis already. This is epsilon into EB. J is equal to epsilon into EB plus 1 minus epsilon into H, considering gray diffuse surfaces. So minus H, and this will be epsilon into EB plus, sorry, minus epsilon into H. Okay. So now if I write Q minus epsilon Q, so this Q I will take from this, okay, so this Q I will take from this one, that is epsilon EB, the second one, okay, and this Q I will take like this. So, okay, so minus epsilon into J minus this, okay. So you can see epsilon into EB minus epsilon into H minus epsilon into J plus epsilon into H. So it will be epsilon into EB minus J. Clear? Okay. So we can write Q into 1 minus epsilon is equal to epsilon into EB minus J. So that means my net heat flux, net radiation heat flux is equal to this 1 minus epsilon by epsilon, right. And if I write the net heat transfer, net radiation, I have to multiply with the area. I can directly write EB minus J 1 by epsilon by A epsilon. And here see what I have considered. Okay, so if I have a particular surface, okay, then for this surface I can draw a node here and a node here. So this node will be EB and this node will be J, and I can draw a resistance. So through this resistance the Q is flowing and this R is equal to 1 minus epsilon by A epsilon. Okay. See, this network is for a single surface. Now if it was a black surface, then my epsilon is 1 and this resistance is becoming 0. Clear? So this resistance is also having a name, but I really apologize that I don't remember the name right now. Okay, so this we can see that we can write the net heat transfer from a surface like this. Okay, now let us see if we have two surfaces. I mean this situation we have drawn here. Okay, let us again, okay, we don't need to draw it again. So we are considering again, that is the heat is flowing from this to this like this. So it is Q1, it is Q1 is equal to minus of Q2. Okay, so this I consider Q1. See here I have also considered my Q is equal to J minus H. The moment I consider that this Q is positive, the moment I consider that this Q is positive, I am considering my J is greater than H. That means my net heat is going out from the surface, because J is the heat that is going out from the surface, H is the heat that is coming into the surface. If J minus H is positive, that means that there is a net radiation heat transfer that is going out from the surface, right. So here again we are considering the same thing. So my Q1 will be, so what I was actually telling is that if I consider for a surface that my net Q is going out from the surface, I am getting my net heat transfer as this, that is EB minus J. Okay, that means if I draw this node and if I draw my heat transfer direction like this, that is indicating that my net heat is going out from the surface. And if I draw my heat transfer direction like this, that is indicating that my heat is going into the surface. And then my equation will be J minus EB. I can still write EB minus J, but then I will get that Q as negative. So here according to that scenario, my Q1 is equal to EB1 minus J1 1 by epsilon 1 minus epsilon 1 by A1 epsilon 1. Nice. Similarly, my Q2 will be J2 minus EB2 by 1 minus epsilon 2 by A2 epsilon 2. And if it is a steady state problem, it should be minus Q1, right? Okay, that is fine. So I write this as Q. I write this directly as Q. Okay, and this as also, okay, so this I also write as Q. No, this is actually, okay, this is also fine, this is also Q. I mean if I take the magnitude. Okay, now finally you see if I talk with J1, okay, so I mean now my objective will be to eliminate these J things, okay, because I am just comfortable with these EB things, because EB I know that EB is equal to sigma T to the power 4, okay. So knowing EB is is equal to knowing T. Okay, so I always want my equations in terms of my Q and EVs, not J's. So how can I eliminate J? Let us see that. So again you see that my Q is equal to J minus H. So I can write Q1 equal to J1 minus H1. So H1 is what here? H1 is, again I can write HO1 plus J2 F21, right? So again if my HO1 is 0, then it is J1 F21. I have also plus J1 F22 plus but that is 0 because F22 is 0, minus J2 F21. Now that is equal to J1 minus J2 equal to F21. Okay, ideally I should have done the whole analysis by multiplying with the A1 here. Okay, that will be actually good. Okay, okay, so I am just omitting the same thing here, but my ultimate concern is that this is my minus Q2. So my Q is, again we can see J1 minus J2 by 1 minus F A1 A2 F21 is equal to J2 minus J1, okay, or I mean minus J2 minus J1, okay, or I mean I can also write this as J1 minus J2 by 1 minus 1 by A1 F12. Now this is a very simple algebra. We have these three equations, right? So we have these three equations. I am just giving you the equations. So let me just copy these equations here. Okay, so I did not copy them. Copy, paste. Okay, this and this fellow. Copy, paste. Okay, so these three equations we have, right? Actually this is also equal to Q1, I was wrong, this is also equal to Q1. Q2 is equal to EB2 minus J2 1 minus epsilon 2. Then see, you are having Q2 equal to minus Q1. Okay, this is also Q1. And this is again also actually Q1. Okay, the moment you write J1 minus J2 equal to, this is equal to Q1. For if you have to get Q2, it will be J2 minus J1. Now if Q1, if you are taking that my this direction is positive, that means Q1 is positive, that means automatically if my T1 is greater than T2, that then my Q1 will be positive, and if you find Q2, then it will be a negative number. So that will not matter. Now you have these three equations, this. I hope that you are intelligent enough to eliminate these j's. Okay, I am just doing this. This is not a very big step. So what you have to do is, see, from this equation you can always write, see, EB1 minus J1 is equal to Q into 1 minus epsilon by A1 epsilon 1. From this equation you can always write J2 minus EB2 is equal to Q into 1 minus epsilon 2, this one, and from this equation you can always write my J1 minus J2 is equal to Q into 1 minus this one. Okay, so add these two guys, so EB1 minus J1 minus J2 minus EB2 is equal to Q into 1 minus epsilon 1, this one, plus 1 minus epsilon 2, this one. So now you put here this, you see you already have J2 minus J1 as this. So you will now have what? EB1 minus EB2 is equal to Q into 1 minus epsilon 1 A1 E1 plus 1 by A1 F12 plus 1 minus epsilon 2 A2 epsilon 2, right? So therefore we will have Q is equal to EB1 minus EB2. By this whole thing I will just copy it and paste it. Okay, this one. So let me delete this. Okay, fine. So now you see that you are now very happy because you have EB1 and EB2. You have this control. Now you can write actually this as this fellow as sigma T1 to the power 4, this fellow as sigma T2 to the power 4. Okay. So now you see that we have 3 resistances and they are being added. So if you have 2 surfaces, each one is having T1 and T2, you will draw the network like this. Okay. So for this surface I have already shown you, if you are considering that the heat is flowing like this, you will have EB1, J1. Then for this surface the heat is going inside, it will have J2, EB2. Now from EB1 to J1, see, this is for one particular surface, that is why this is called the surface resistance. So by God's grace I have already remembered the name. So this is R surface 1, okay, and this is the space resistance, R space. So this is again the surface resistance, this is R surface 2. Clear? Now you know that my R surface I is equal to 1 minus epsilon I by AI epsilon I, and my R space Ij is equal to 1 by AI Fij, or is equal to 1 by Aj Fji. Clear? So this is how you have to draw these things, and this is called the surface resistance, this guy is called the surface resistance, and this is the space resistance. You see, if you have black bodies, then this part will not be there and J1 will be equal to EB1 and J2 will be equal to EB2. Okay. So now you tell me, if you have now again 3 surfaces, okay, again the same thing, 3 surfaces, okay. So each one is having T1, T2, T3, but now this time these are not black ones. Again you have to draw 3 nodes, okay. So this will be EB1, this will be EB2, this will be EB3. So firstly from EB1 you will draw something called J1, and this will be R surface 1, right. Then again from EB2 you need to go to J2, this will be R surface 2, and then again from EB3 you have to go to J3, this is R surface 3. Now this J1, okay, now see, space resistance is actually the connection between the 2 surfaces. This sentence is very important, please be very focused. That is, the space resistance is building the connection between the 2 surfaces, and the surface resistance is only yours. I mean, if I compare that, uh, there is something that is totally yours. Uh, you will not share that thing with anyone else, but there is something that you are bound to share with everyone in the group. So this space resistance you have to share with everyone in the group, but the surface resistance is only yours. Okay. So for non-gray surfaces, if you want to share something, then firstly you have to uh, show your property. So this is the surface resistance. So if you, I mean this EB1, this is not the surface here. So this J1 is the representative of the surface through which you have to draw the other networks. So now you can draw like this and this. So here we have our space SP 13, R SP23, R SP 12 or 21. Okay. So this is the radiation network for a non-black surface enclosure, triangular enclosure. So I mean, like that you can draw for any number of surfaces. So if there are 4 surfaces, what do you have to do? See, I mean, if you have one more surface like this EB4, just from EB4 go to J4 like this, and you have to build 3 more connections. So one with this, one with this, and one with this. And from J1 also you have to build 3 connections. One is this, and one is this, that is already made. From J3 there are 3, this. Okay. So likewise you can make the radiation network between any 2 surfaces. Okay. So this was very critical. If you are appearing for GATE, this is very important, and I mean, even if you are not appearing for GATE, this is important for M.Tech and PhD people also. Okay. So this is the radiation network theory. I mean, this is the analogy with the electrical networks. Okay. So this was, I think, a short lecture. So from the next lecture, we will solve some problems, and which will show you the applications of these 2 theories. One is the simultaneous equation theory, another is the radiation network theory. Okay, then until that lecture, goodbye, take care, and thank you.